Welcome everyone to this week's prime-time seminar. Today's speaker is Sourish. He's an integrated PhD student in the department. He'll be talking about the giant in Erdös and Rényi random graphs. Thank you, Ajay. So, random graph is an object introduced by Erdös and Alfréd Rényi in 1959. They published a series of papers from 1959 which talked about something I'll be discussing today. So, the object they introduced was called, and is known today as the Erdös and Rényi random graph. Since then, there have been multiple models proposed to study different properties of random graph. Since they come up in quite a different scenarios like social networks, computer networks, and epidemiology, and in the fertile field of research even today. Okay, so let's start off. So I'll just write a tentative map of what this introduction, which will lay down the basic notation and concepts, which we'll keep on using. Then we'll move on to the main results. We'll just a slight detour and look at branching processes. Come back to the sketch of group. If time permits, I'll talk a little bit more about other models. So to start off, G will denote a graph. So this is the vertex set. Almost always we'll use this box n is defined as nothing but one up to n. So almost always our vertex set will be n, and this will be h set. So this is the notation we'll use. So graph is nothing but just a set of vertices and the relation which will be known as. And this will always be a simple undirected graph, that is, edges don't have any ordering. There can be an isolated edge as well, but it doesn't matter. Let me start the first definition. It's not ordering. Yes. No, it's undirected. So if I call this one, then edge will just be denoted by what which source? Yeah, it's the same. It's kind of a. The first definition. This is this. So there are two parameters to this. So in the natural numbers and a parameter p in 0 to 1. A random graph So what I mean by a random graph is that just consider a collection of graphs and I introduce some sort of measure on them, which turns out to be a probability measure. So let's say I consider all graphs on n vertices and pick uniformly among them. Since it is a graph on n vertices, there are finitely many among them. So I can assign a uniform measure on it. So that would be a kind of random. So I'm introducing a new kind. So I'm telling you what an Erdös and Rényi random graph is, or how do you pick a random graph from this set of n graphs. Erdös and Rényi random graphs if each H is present with probability P independent. P independent. So that is so this will always mean that I is connected to J. So there exists an edge between I to J. So this is how I denote. Rather than use is connected to J equals P for all I comma J predominant system. So this is just to keep it complete. I won't be allowing any loops or multiple edges. And I'll denote it as I mean, it doesn't really matter if I write it or not, because I'm not allowing loops and all. So this is how I'll denote an Erdös and random graph with H probability P and vertex set N. With regards to this, I'll define something as CP. So this is the connected component that G will then use. So for example, if I add a few more vertices, so your graph can always form a set of disconnected components because I'm not forcing any condition of connectedness upon them. So you will get these three big components, and now let's say this is B. Then this entire thing is B of B, the component of B, the connected component of B. I'll always say component from now on, and it will always mean the connected component. So you can denote this as B component. This notation means that there exists a path from U to B in the graph via edges. So in this, let's say this belongs to the connected component, so you can go via these two edges. So this is the connected component, and the main object of interest today will be maps. So I can always find this in the maps. So I can define this object. But to define this object, I need something more because there could be more than one component having the same amount of vertices or the maximum amount of vertices. So I'll just break ties by declaring that the component having the smallest index is the largest. So let's say the component of 1 and 2 both have, let's say 10 vertices, and they are the largest, and they don't intersect. And I just declare the component of 1 to be the largest. So just to break ties, make it easy. The 1 containing the smallest index. By index, I mean I'll always label the vertices from start. Now it should be outside. Sorry, modular should be outside of max. Max should be inside. Need not be. TV is the condition, just defining this to be the size of the set. So that is a set. Maximum on those sizes. There will be a set of numbers. The maximum amount. Just to make the largest component unique in some sense. Cmax is a number. Mod Cmax is a number. Cmax is the set. Yeah, Cmax is the set. I mean, I should have defined this one first time. notation I'll be using? Because big O of G of M. Okay. Yeah. There's equal some constant. But larger than the constant. And this constancy does not depend on M. Second notation I will use in the present. I don't think this will be clear, but I'm just defining this thing here. Okay. Then get GM goes to views. Okay. So what I want to study is N, lambda comma. I want to study the evolution of this graph as N increases. I'll fix some parameter lambda. Lambda greater than C. Now I want to know how C max behaves, or the size of C max is as I increase N, depending upon lambda. So I want to know the asymptotic behavior of C max as N increases. And to study the dependence of lambda. Especially about lambda. So this is a regime called sparse graphs, and I mean, don't have any reason to why study lambda over N. This lambda will be the expected limit, so it will be a yeah, that is expected. That's so you know what happens. So you can't. If I say it right now, that won't be a okay. I mean, yeah, I can say that since so what happens is that the degree distribution of this particular series goes to Poisson lambda. So now I want to study graphs of, let's say, which have this degree distribution. Then so this provides a good approximation of what the largest component is. Or B is greater than what is equal to? B is equal to B is equal to lambda. This parameter is what I'm saying when B is greater than lambda, probably that the graph is correct. Question 1. There is some equal. Lambda is equal to lambda. But lambda, which lambda? The threshold lambda. It's not fixed. Lambda is fixed a priori. No, that is true. That is true, but then what is the threshold? Yeah, I mean, if you take lambda to be log n by n, then now it makes just log. So now just log. Oh yeah, sorry, lambda log n. That will become over n. So if you take this, then what kind of result you have is n 1 minus epsilon of n by n is almost surely disconnected. For large or whatever. Disconnected with hyperwave. And the n 1 plus 1 is connected with hyperwave. This is not what we'll be discussing today. You are fixing lambda as constant. Yes. But we discussing is so meaning with aim with first is lambda is less than 1, then or of the order log n. Lambda is greater than 1. So we go in this data. That just means is some constant kind of. So from both sides, I'm not using big or small. Okay. I'll use big or small. Yeah. Fine. And finally, for the threshold, so you have double jump kind of thing. So in this regime, there's some particular behavior. They're plotting this point, then this regime becomes the order. So something surprising impact for the third case is that all components are of the order n2. So you have that for lambda less than 1. So you can think of it as some sort of evolution. So as lambda keeps increasing, the components keep increasing, become of the same order, and at some point around 1, above 1, one component breaks out and occupies all vertices, and all others shrink them. We'll be discussing the third part because the techniques I'll be discussing about branching processes are relevant only for the first and second case. The third case uses martingale theory and some standards, so that is a bit more involved. Yes. Imagine no. Let's just see. Okay, so yeah, C is less than always. This in this case, C is less. Can't be greater than 1. Some point it will become 1 at particularly that point. So let's start branching process. What is the branching process? So this is the model used to describe population evolution in a particular. What you have is that you have a distribution. Is a discrete distribution of natural growth or other non-negative. Nature. What do I mean by this? So start off with a rule. Let's call this rule. Now I sample this distribution. Let's say from sample mu again for both of these. And this is 0. zeros. Let's say this diagram. This is the branching process. The thing governing it is this constant. Why am I talking about branching process? You can see the way I'm building this branching process. Then you can use it. I'll discuss what this precisely means. You can use it to build this Erdös and random graph. Let's say you fix a vertex. Let's say you start from 1. Then what happens is that you can check how many neighbors it has. So you can check how many neighbors it has, move to the next node, and check how many neighbors it has, and so on. And you can try to find what the components are. So this is just an idea. Let me try to make it. And start labeling this. So what I do is that something called as what I'm doing is I count the number of active vertices that branching. Let's say I start from 0. So I'll explore this, I'll find these two words. On these two I'll be able to. Since I've lost 1 and gained 2, I'll just add 2. So 1 which has 2 vertices. Since I've lost 1, then I'll find 2. So how in this now? This is called the breadth-first experiment. So the vertices in order of plus 3 is given. So I'll add 3. It will come back.
Sourish, are you exploring breadth first in the breadth first way? Yeah, so I think then the labeling is the labeling fine?
Yes.
Okay.
Now I've explored 3. If there are more children, I'll go down by 1. 4 again, I'll go children. 1 down. We'll call as the random of exploration of this branching process. What we will notice is that the number of steps and number of steps tells you the number of vertices at each point. So whenever I hit 0, that means I explored all. Each point I'm exploring exactly 1 vertex. This length will tell me the number of vertices in the branch, size of the branch. So this correspondence will help me to ascertain this mod ceilings. So that's why this branching process is useful. In fact, there is something convincing which tells you that the branching process is the correct object to look at. I'll make it more precise, but what I mean is that I can do similar sort of exploration for random graph. I'll come back to that. So one of the primary questions in branching processes one can ask is, as you keep increasing n, or you keep iterating this process, in this case I just can get third generation. But what if I ask you what happens as n tends to infinity? Does the branching process survive? By survive, I mean, does it keep on going till infinity? Or does it end at some finite point? So what do you think this property depends on? Guesses? Yeah, mu. But any particular property of mu?
The expectation.
Yeah, so the expectation. So let's say the expected number of children is less than 1. What will happen then? When in all likelihood, it will die out pretty quickly. And what if the expected number of children is greater than 1? Even then, it might survive, but there's still this non-negative probability of, depends on the extinction probability is not necessarily 0, even if expectation is greater than 1. Another thing is, what do you think happens to the expectation of x equals? Oh yeah, mu. Equal to. Yeah. So there's a case where you can just define your distribution to be each vertex has one child precisely, and that has expectation 1, and that will keep. But apart from that, extinction probability is in fact 0 or 1. Sorry. So it does die out with probability. So let x follow mu. X equal 1 and less than 1 implies probability branching process alternated by diagram. Once expectation x is greater than 1 implies probability alpha less than 1 and finally x equal to 1, but probability of x equal 1 is less than 1.
Sourish,
Yes.
in the second case, if I remember correctly, are there not any other assumptions? There was some theorem like Kesten and Stigum, I think, if I remember correctly. It's I think you need some x log x to the moment of x log x to be finite for the probability to be less than 1. Otherwise, it dies out. I mean, with probability 1, I think.
For greater than 1.
Yeah, for greater than 1, if the expectation of x log x is finite, then I think this process dies out with probability less than 1. But otherwise it should die out with probability 1, I think. If I'm remembering correctly, there's a theorem due to Kesten and Stigum.
No, as far as I remember, the proof goes through generating functions. And if you plot that curve, so of the generating function, it has this intersection before 1.
Yeah.
Whenever your expectation. So I don't think you need this additional condition.
Okay, thanks. Yeah.
So now try to compare over here. So if you note that, so what the average degree turns out to be is, so average degree is in some sense the average number of neighbors. So n times lambda by n turns out to be lambda. And look at the conditions on lambda over here. So lambda less than 1 is showing some particular behavior to compare it with that ratio. Lambda greater than 1 is showing some behavior. And this, as I told you, utilizes some other techniques. So this prompts you to look at branching processes more carefully, and if you can utilize it for random graph, particularly Erdös and Alfréd. Now let's move on to the sketch the two. How much time do you have? So I'll just sketch the idea. I will not go into any of the pro. Whatever I use, you know. Okay, so let me try to make this SL more. So this exploration, what this exploration process looks like is x n plus s n minus 1 minus 1. So the state of the process, I add the number of children of the current vertex to the previous state of the process and subtract 1 since I am exploring that vertex itself. So this will be quite important. Exploration of Erdös and Alfréd. So what I do is, let's say I start from vertex 1. So now I have n minus 1 many neighbors to choose from, and each of them has a connection probability of lambda by n. So the number of children of 1 would be binomial n minus 1 comma lambda by n. This is how I start off. Let's say this I have 3 children. Label them completely, since labeling is immaterial in this case. Now, if you notice x for x2, the number of children is reduced. It cannot have n minus 1 many again, because already you have explored 3 vertices. So those you cannot explore again in this process. So what will happen is that you get minus 4 lambda 1. And this will keep on happening. As you explore more vertices, your exploration method, the offspring distribution will keep changing at each instant. And these number of vertices will keep dying out. So if you notice for branching process, this phenomenon does not occur. Your distribution of xn is IID, that offspring distribution mu. But over here, there is some effect of this past exploration on this process. So what you can argue in this case is that for small enough, timeline, you can argue that the number of vertices are small. So n minus a behaves like n. So what this approximation is, I'll keep it vague for the time being. But you can see that hence it does kind of behave like a branching process with binomial n comma lambda by n. Sorry. What I mean is that what I want to keep track of is the number of children. So let's say there exists an edge between 2 and 3. It won't really affect your size of the component because you have already explored it. You know it is in the component. So let's say there does exist an edge between 2 and 3 and 2 and 4. But once you have explored it from 1, these edges don't really matter because the size remains unchanged. You want to keep track of the size of the component. That is the number of vertices. So you only want to know which new vertices are coming in. You don't really care if there are any edges between the already explored vertices. That depends on the breadth first exploration. You can choose whichever way you want, but it doesn't affect the distribution as such. Even if they are, that's what I'm saying. Let's say 2 and 3 have a common child. I'm exploring 2. Let's say I find some other vertex 5. Now it doesn't really matter if 3 and 5 are connected because that doesn't add any new vertex to the process. I will remove it. So whenever I explore X, I'll explore 2 first. So now once I get 5, I'll remove it from the distribution. So I'll get n minus 5 lambda over. Removing 5 from the set of available vertices. Sum of Bernoulli. That is joining. Binomial NP branching. What I mean by this is that offspring distribution is NP. Sorry, binomial N. The important result in this case is that C1, that is the component of 1. I'm not saying Cmax at this point. The size of the component of 1 being greater equal to P is upper bounded by the size of equal. Now why this? So I can couple these two. What I mean by couple is that I can start a common process. Let's say I declare 1 to be the root of the branching process and the vertex 1 in the Erdös and Alfréd random graph. Then what I get is that the distribution of offsprings of 1 in the branching process is binomial NP, and the distribution of neighbors in the Erdös and Alfréd random graph is binomial n minus 1 lambda. Okay, let me make it lambda over n. So if you see, already the available number of children to the branching processes is more. And as you keep exploring this, keep growing this process, the number of children available to each vertex in the random graph keeps decreasing. But for the branching process, it still remains IID binomial n. So there are n, there could be n many children at each instance. For the random graph, they keep decreasing. So this result should be kind of believable. Is that okay? So what I mean is that at each instance, the random graph will have n binomial n minus k lambda over n, but the branching process will have n lambda over n. So n minus k is less than n. I know that is not a sound justification, but you'll have to believe me for now. So it's something called stochastic domination. So that's what happens. The second thing is, you now want to get a lower bound as well. Less equal.
you know, binomial n minus a lower n. Greater equal to greater equal so why this? What I do in this case is that I see first time the number of remaining components are k, n minus k, and up until that time, I if you so when I start off this branching process, it will always have n minus k, but till the point the number of remaining vertices hit n minus k, the random graph has more than n minus k many options available. So what I mean is that at each instance, your number of available vertices keep decreasing, but I keep track till what point does it stay above n minus k. And up until that point, this branching process is stochastically dominated by the number of neighbors in this. Till the remaining number of vertices in the progression of E and lower n is how n minus k x I equal this. So let's say at each instance I explore this, the number of children is xi less. So this is because the number of parameters this has is n minus k, but this has more than n minus k many neighbors available. If you notice, this is not exactly stochastic domination because for each k you have a different branching graph. Here the process was independent of k, but here it depends on this. This is not exact stochastic domination. So for each k there is a different branching process. That's the two important results we need. Now let's start doing the main results, or rather doing just seeing how they are proved. Fetch two or one. Known as the super critical zone. So first we have upper bound for the subcritical region. What this upper bound is for every k greater than 0, where delta greater than 0 is fine. Not minimum greater than 2 logs n of the order. So as n increases, this will approach 0. That will tell you that it can't be too big than log n. This is not this A is not exactly greater than 0, but we'll see what it is. I change it as we proceed. For the upper bound, the proof is quite simple. What you're doing is that you use that stochastic combination right away. So what you will get is that if you put k equals k log n, you use this stochastic combination to study what a binomial branching process. When does a binomial branching process have size greater or equal to k? So let's say I define t. Like when Sn is 0 for the first time, get the number of vertices in the branching process and the number of children or the number of vertices for so since I defined Sn for both the branching process and the Erdös and random graph, whenever Sn hits 0 for the branching process exploration, I get how many number of children or the total progeny in the branching process. For the random graph, the size of the compound. So as I said, the probability of T just the probability of X. Right. Because I want this process to stay above 0. Since whenever this hits 0, it tells you the number of size of the branching process. So these two are equal. Now if you keep iterating the formula for Sn in that one, what you get is K equals R equals 1 to K. So you keep expanding that formula for Sn in that. Here, what we have is that Sk in this case is T in this case is a binomial and lambda over each of the x's is a binomial n of n comma lambda over n random variable. So what you want probability now there is something called large deviations in probability, which tells you the probability of for binomial it's quite it says that this constant depending on number, depending on n naught. What is probability of not seeing it? It's you can count. This is same set as union. I Oh yeah. Once I plug yeah, this I used to get this. This was yeah, this I used this. I used this. And now you want this quantity to be relative. If you want this to switch. Now I have to restrict K. That's one. That thing would be relative quantity, and you can take that to be lambda. Delta. Sorry. Now there is a lower bound. For the upper bound for the subcritical rate. In interest of time, I'll just keep lower bound for now. Then this result has been proven. Lower bound also uses this. Yeah, this one. But I need to introduce a few more concepts, but I want to avoid that. Should I do that? Should I complete subcritical or should I move to super? Should I complete subcritical? Oh, okay. Okay, I'll complete. So I'll introduce something called Z greater equal to. So this counts the number of vertices contained in components of size either equal to and also state it as Newton indicator on either equal. Okay. So what this? Yeah. So it's not just positive, it's lower bound equals. You'll say. Yeah, I'll have to change that. This quantity. So why is this important? Because what I can define is that P max is equal to the max P square. Sorry, divided by P is bigger. So what this means is that let's say you cross over the size of C max, then none of the vertices will be contained in a component of size greater or equal K. So this will become 0 in that case. So it will peak out or it will stay positive till the time it hits C. After that, it will just go 0. Because none of the indicators will be 1 in that case. Let's say mod CV is greater or equal mod C max, then strictly greater than mod C max, then it is, no such vertex. Just take a few more minutes. So what I mean is this modification of Chebyshev inequality. Twice, yes, equal. Sigma square. This is the variance of x over no? Modification of Chebyshev inequality. This is the mod of schema in less than if you look at this, as I said that if it crosses C max, then it will be 0. So if mod C max is less than K, then there will be no vertex such that this relation, there will be any vertex of this case. Now at the end, I'll just put K into the line. So since I want to use this on this, the particular reason I have chosen this step. So now I need two things for this: an estimate for the variance and an estimate for the expectation. So the estimate for variance turns out to be there. That is what you can for 10 times. Estimate for variance. This quantity. called PIR node. So this comes because of again one of the this lower bound. And yeah, I have the same as the last. Here, I want this. I guess I overplanned a few things, but that's it. All for now. Yeah. Thank you for your patience. Sorry for going overboard. Well, not exception for Rényi. Actually, what you mean to say is that there is an explicit constant involved for this. And then